Hi everyone, welcome to a new video about hydraulics and pneumatics. It is the last video, and in this video we will discuss more of the basic components in hydraulics and pneumatics. So in the previous lecture we discussed the main difference between hydraulics and pneumatics. And in pneumatics the fluid is compressible, and in hydraulics the fluid isn't compressible, so it's a liquid. And we discussed some working principles, mainly of compressor and pumps. And from there, you learned how to describe a compressor cycle, and you learned to determine the amount of air that is required in a certain process. And this is a process which has, for instance, an increased temperature or pressure. Well, and you learn to determine the moisture content of air, which is important in pneumatic processes. In this lecture, you will learn to describe the working principles of hydraulic and pneumatic valves. So these valves will enable to control the flow. You are able to describe the layout of hydraulic and pneumatic cylinders, and you will learn to make simple hydraulic and pneumatic diagrams. And for this you need some knowledge about cylinders and valves, and mostly of valves. And in the end you're able to design and calculate the layout of a hydraulic and pneumatic process. And this learning objective is only treated to a limited amount and mostly based on cylinders. Okay, now we'll start with discussing cylinders, and well, we have hydraulic and pneumatic cylinders, and the differences. There are some differences, since for oil you will need for liquids you will need other seals and maybe a slightly altered layout compared to a cylinder, which can be used for moving gases. But the basic layout is fairly the same. And hydraulic and pneumatic cylinders are used for linear motion, so that is motion in one direction. And like you can see over here at the excavator, there are two cylinders over there at the blue arrow, and they can only move in the direction of the cylinder itself. And the same happens at the other cylinder, and there's one cylinder on top as well. So there are no other possibilities of moving the cylinder. But of course it can extend and it can retract. So there's motion possible in only one direction. But there are many varieties of cylinders and many clever applications of cylinders. And I guess since you're all very intelligent students, who ought to be, you're all able to come up with more varieties of these cylinders, depending on applications, of course. So let's continue and discuss the layout of a cylinder. And like you can see over here, I brought the cylinder. I think this one is especially used for air, but the basic principles do not differ a lot from hydraulic cylinders. So let's discuss these. The most important part of the cylinder is the piston, and this piston is connected to a piston rod, and of course it's mounted within the cylinder, and the cylinder has a casing or a housing, and there are two ports, port A and port B, and these ports allow flow going in or out the cylinder. And you have one port on the head side of the cylinder and one port on the rod side of the cylinder. To keep the head and the rod side gap together, we've got a tensioner over here, and that is very specific for this cylinder, since it uses tensioners to keep everything together. But there are many other ways to assemble a cylinder, so the tensioners are not really generally used. What is generally used are the And like you can see on the image on the top left, are wear rings. So of course, due to motion, there will always be friction, and wear rings are used to decrease the amount of friction. And there are seals to prevent oil or air from leaking over the piston. And the same happens at the rod side cap. There are seals and wearings. And over here you see a scraper as well. The scraper is usually used in hydraulic appliances to prevent oil from moving to the outside of the cylinder um, and giving a lot of mess. So that's what scrapers are used for. But so in pneumatic cylinders, these are not always used. So let's go to the next slide. There are two important varieties of cylinders. The first are single acting cylinders, and they are actuated in only one direction. So in fact, they're only able to, for instance, extend, and retraction has to happen using an external force. For instance, a mass. So by the weight of some mass, the cylinder can return back to the original position, or using a spring. So that's a single acting cylinder. So it only has one actuated side of the cylinder. And we have the double acting cylinders. And like you can see over here is an animation. The fluid pressure is used for both extension and retraction, and that's convenient when you have, for instance, a horizontal movement, or when you need to actuate a process in two directions. So like you can see over here, pressure is on the head side of the piston, and on the rod side of the piston as well. Okay, so and these are the main cylinders, and there are many varieties to these, but these are the most important ones. And usually any other cylinder is just an intelligently tuned double acting or single acting cylinder. So. And here are some examples of varieties. For instance, the telescopic cylinder, like you can see over here. And please note that this is a single acting cylinder in this case. It doesn't always need to be, but in this case it's a single acting cylinder, and it's activated by the weight of this dump truck. And on the bottom you can see a magnetic cylinder. It has a piston that carries a magnet, and on the outside of the cylinder there's some sliding mechanism, which is a magnet as well. So it's connected to the piston and by a magnet. So we have an outside slider, a slider moving on the outside of the cylinder because of magnetic forces. Well, and one more variety, and then I'll stop mentioning varieties of cylinders, is this one. This one is a cylinder, I think it's a double acting cylinder, of which the piston moves in a horizontal plane, but both clamps at the end of the cylinder move in a vertical fashion. So they move in different directions, and it's just designed by making clever use of the properties of a double acting cylinder. So for you as engineers, maybe the most important thing is to determine the cylinder force, especially when you want to choose the cylinders you need, and it's always convenient to choose standardized cylinders, since these will usually be relatively cheap, and all cylinders you see in this lecture, I think they're all standardized, so you won't need to make these by yourself. So the first thing we of course need to take care of is our statics and dynamics. And of course you all know that the force depends on mass, on friction in our case, because we're usually moving things or clamping things, and on the acceleration. So yeah, we have some force, we have a friction, and we have a normal force. That of course depends on mass. But what matters as well is uh, the method you use for accelerating your system. So you need to take in reducing or increasing forces, you need to take care of this. How are you going to accelerate? And you can really think about this. Well, of course, this friction factor can be changed as well by choosing different materials or guidance, or use roller bearings or sliding bearings or whatever to decrease the friction factor. So that would all be well engineering you can do before you even start choosing the cylinder itself. Over here, what you need to take care of, if we have a cylinder that needs to deliver a horizontal force, of course, if you start applying a vertical load, it will have consequences for the cylinder and for the size of the cylinder you will need. So always take care of your design before you are going to actually choose a cylinder. So over here you see that the force F1 at the end of the cylinder rod causes force to the seals and scrapers and whatever is there in the cylinder head. And may cause some moments as well, I'm not sure. So proper design for load case can be very beneficial for the design of your cylinders. And this is solved, it can be solved, for instance, using this method. You can see a cylinder over here, and we have two guidance units over here. So these two, they'll guide the object in a straight manner, so to reduce friction and allow you to use a smaller and probably cheaper cylinder. So what matters as well is the application you use it for. Do you use it for clamping? Then the maximum force has to be delivered at the end of the cylinder. So when you're actually holding something at the end of the stroke, whereas in punching, we'll already need to deliver some force starting the punching process, but a large force has to be delivered at the end of the process as well. And I think that's even the largest force, so you need to take care of this. And when moving something in a dynamic situation, then the maximum force has to be delivered during maximum acceleration. So you need to take care of that and rethink that. And to ensure a smooth process, we have this load ratio. And this load ratio is the theoretical force which you just have defined, divided by the required force. That your cylinder, and this required force you're going to use to choose your cylinder, and there's a load ratio. And this load ratio it depends a bit on the case, but it's used for smooth operations. And well, let me show you over here. Here we have a seal or a how do you call it? Well, these contact units. And we have a cylinder rod. So over here we have a rod, and over here we have a seal. And of course there's friction between those two. And to and that will hinder the movement of the rod and therefore the cylinder. So to have smooth operations, you'll need some extra force, and that's defined using the load ratio. And the load ratio is defined for horizontal and vertical operations, and it depends, of course, a bit on the case. But in horizontal operations, this load ratio is usually 0.7, and in vertical operations a little lower, 0.5. So you will need 0.5, 1.5 times the theoretical force for the required force in vertical operations. So then, when actually choosing the cylinder itself, of course, the thing that really characterizes your cylinder is the area of the piston, and you can easily define that using the formula for force, pressure, and area. Keep in mind that for double-acting cylinders, the rod side piston, the surface of the rod side piston isn't as large as the surface of the head side piston. And this has a consequence that the force in the retracting stroke may be lower. So you need to take care in which stroke the amount of force is most important. There's some solutions to it. For instance, there are double-acting cylinders which have actually a rod on two sides like this. So then, if it's really important to deliver the same force in both strokes, then this can be used. Or you can just choose your cylinder based on the rod side area and diminish the amount of flow or reduce the pressure by some valves or whatever to get a comparable action in the extending and retracting stroke. One thing that is important, but I'm not going to really discuss in detail, is the amount of kinetic energy you want your cylinder cap to absorb. You can imagine that if there's a lot of velocity that it needs to be stopped at the end of a stroke. So in this way you can see the retracting stroke in which the cylinder, in which a piston over here is going to move back to the cap. In this case, an air cushion is used to break down, to absorb the kinetic energy, and you can see it over here. And now air, it's in the retracting stroke, and you can see the air flowing out through this large port over here. But in the next stage, you can see that this port is actually blocked over here. So air can't go out through that way anymore, so it has to go to this small port over here. And of course, that will lead to an increase in pressure on this side of the piston, and therefore the retracting stroke will be decelerated, and it will end very smoothly to the end of the cylinder. So this is one method of to keep in mind, or to reduce the amount of kinetic energy to the back of the cylinder, to the cap end. And this can actually be really useful if you have a cylinder which you want to have really small, really lightweight, and then can be useful to reduce the cap thickness and use a method like this to reduce the amount of kinetic energy that the cap has to absorb. So, and if you choose a cylinder, you can usually do this from a table from whatever manufacturer you like, while keeping in mind the methods to determine the cylinder size. You can see the size of the bore at the rod side and of the head side. And of course, choose your pressure of the compressor or hydraulic pump or whatever. So now we're going to the next components I would like to discuss, the valves. And valves are used for controlling the flow rate and that with the velocity of your components. So you can maybe imagine if the flow rate is really high, that the velocity of some cylinder will be really high as well. And if you want to control this, for instance, to reduce the impact of a cylinder, then we need to control the flow rate. You can control pressure. So if you want to reduce the amount of force a cylinder exerts on some product, we will have to reduce the amount of pressure. But it's probably the most important function of valves is to change the direction of flow. So the routing of the flow. Choose other hoses or lines to pump the fluid through. So, and we're actually going to focus on this. And in the end, I will tell you something about reducing the flow rate. So let's go to the next slide. Okay, let's start with the. I forgot to run my animation properly. I'm sorry. Let's start with this one. Over here we have a single acting cylinder which is retracted using a spring and extended using I think it's air or maybe oil pressure. It doesn't really matter now. And there's a valve, and like you can see over here, we have fluid going in. Maybe you can see it over here. Yes, we have fluid going in at the pressure side, P, and going through hose A into the cylinder, and we have the retour hose at P. And well, if we want to characterize valves like this, you can do this using the amount of ports that are connections of a certain valve and the methods of operating this valve, of using this valve. And in this case, you can see that there are 3 ports connected and that there are 2 ways of using the valve. We can either connect the port side to the A hose, and we can connect the retour to the A hose. So there are 2 ways of operating this valve, and thereby we call this the 3-2 valve. So it's this valve. Okay, well, let's go to the 5-2 valve, although I didn't expect to do this the other way. Let's show it. So over here we have a double acting cylinder. Now we have the pressure side in the middle and 2 retour hoses. Or if it's pneumatics, it can even just be a vent. So we can blow the air off. It doesn't need to go back to any reservoir or something like that. Now we have got 2 outgoing hoses, A and B. And well, like you can see, we have 5 connections now. And we have, again, 2 ways of operating this valve. So we have a 5-2 valve. Okay, and from this, we want to schematically represent the valves. Because you can imagine that it's a tedious process to continuously draw these valves. So we're going to draw them a little faster using schematic representation of these. And valves are usually represented by blocks, and the number of blocks tells you something about the number of ways of operating a certain valve. And we use arrows to indicate the direction of flow. So like this. So you can see you can see a flow going from A to B, and you can see at C that the flow is actually blocked. So this indicates a blocked flow, and this indicates a flow from B to C, and C will probably be some retour valve, and now A is blocked. Because the piping, when drawing the schematic representation of valves, piping is always connected to the rest position. So let's assume that we've got it in our cylinder, our 3-2 cylinder we discussed before, is in rest now. So we have two options. So it will be a two-plug cylinder with the pressure, the A, and the retour. So from the pressure to the A, that's apparently my rest positioning. This is how I have to draw it. There's an ingoing hose over here, and there one as well. That one is blocked in rest, and this one will flow to the hose A, so to the cylinder. So this is how we actually draw these schematic valves. So are we there yet? No, we're not completely there yet, because we need to indicate the method of operation. And that's usually drawn on the left-hand side. And there are many methods of operation, and I show you only a few of them. You can. I'm sorry, by the way. I'm sorry, it's in Dutch, but couldn't find any better in English. But you can, in the left column, you can see the methods you can use for operating this in manually, or in the second row, you can see how this is column. You can see how this is done mechanically. It can even be controlled by air or electrically or magnetic. There are many methods to operate these valves. And well, in our case, it's operated by a button, so the red button. We draw it on the left hand side, so we draw it like this. That's already a bit better schematic representation. Only there's one more thing we need to take care of, and that is when is a valve stable? So what will be its rest position? Will it be the position? Does it have a standardized rest position? So if I release the button, will it go to another position, the position it used to have before, or will it remain in this position? Well, we call this mono or bistable. So a monostable valve is only stable in one position. So if you control the valve and you leave it, it will go back to its rest position. Then you have to draw a spring on the right hand, and if you have more than two valves on the left hand side as well, and you indicate the side to be pushed with an arrow. And if it's bistable, it's stable in multiple positions, then you need to draw an arrow in both positions so that you actually can see that it's activated. So let's assume it's monostable, so it's stable in this position that's indicated now in its rest position. Then we have to draw a spring on the right hand side, and it's clear that it's monostable, so it will go back to its rest position after you release the button. Okay, and of course, a force is required to move the valve to an activated position. Okay, this slide shouldn't be here. Okay, well, let's do some small exercise together. I've got a wheel loader over here, and I'm actually very interested in this cylinder. I want to draw the flow, the hydraulic flow diagram of this cylinder. And well, from what I know, it's a double-acting cylinder, since this the bucket of this wheel loader has to deliver a power stroke when going up and when going down. So it's a double-acting cylinder. And when the operator does not touch the handle, the bucket should remain in its position. And of course, I challenge you to start working on this assignment first by yourself. So draw the cylinder, the pump, and whatever you think is required, and of course the valves, and think about how about the flow diagram. So draw it yourself, and I hope you'll get as far as I get. So please try it yourself, and after that you can continue the video. So I'm very happy that you tried this yourself. Now I'm going to show you what I did. So first I'm going to start with drawing this cylinder, and on the left hand side I draw the pump. So this is the symbol, the schematic representation of a pump. On the right hand side, and I think that's really clever, it's a relief valve, or it's a reservoir, an open reservoir to which we can return the oil. And when talking about hydraulic appliances, you always need to think about how to return the oil, because you can't spill any oil. That's forbidden in general life. Okay, so we have our cylinder on top, we have a pump on the bottom left, and we have a reservoir on the bottom right. So let's continue, because I actually know that this it's a double acting cylinder, so I need at least two different flow directions, extending and retracting, and I need a rest position as well. So it will be a valve offering me three options. And so it will look like this. And we have some pressure flow coming from the pump. We have a return flow going to the reservoir, and we have A and B, flows A and B. And so it has four connections. So we have a 4-3 valve. Okay, and from what I know, it's monostable, since it will always, as soon as the operator leaves the handle, it will return to its original position. So we can draw springs on both sides, and the operator is going to operate it using some button or some handle. I don't actually know, but it's gonna be operated manually. So this is how I draw my manually operated monostable 4-3 valve. Okay, and now I'm going to, in the rest position, the cylinder will be blocked, so it will look like this. So no flow can go in or can go out. And in hydraulics, you can represent it like this, since we know that oil can't be compressed, or only up to a very limited amount. So we know that this is sufficient to keep the bucket into position. There is a problem, however. If I have a pump in this wheel loader running, and I block the flow, then of course my hoses and whatever wouldn't live very long. So I'm going to do something I think is really clever. I'm going to connect the pressure valve in the rest position directly to the return valve. So like this. So when the cylinder is not activated, so oil is directly pumped to the return valve. And if you it's usually the process of activating the pump and switching it off is usually less efficient than just pumping the oil around. So the pump can work at a stationary or at a certain fixed amount of power. That's better than switching it off and on for the pump itself. Well, I think the rest is fairly easy. When the operator pushes the handle, I want the cylinder to extend. So the pressure side has to be. I'm joking. When the operator pushes the button, I want this cylinder to retract. So I connect pressure side to the B hose and the return valve to the A hose. So it will look like this. And when the operator pulls the manual controlled valve, I want the how do you call it, the cylinder to expand. So then I'm going to connect the pressure directly to A and read to the B. So it will look like this. And so let's check whether it's correct. And like you can see over here, this is what the real flow diagram looks like. It's actually from the book my granddad used to use when he was learning his hydraulics. And the drawing that belongs to this is this. And over here you can see the valve itself. It's over here. You can see the pump over here, so and pumps over there as well. And like you can see, there's one large reservoir, so the pump needs to get this oil from somewhere as well, so it is the same reservoir. And there are some filters over there as well, so these are the filters that are over here. And there's one thing that we haven't discussed yet, and we're going to discuss it now, that are these. Yeah, I think they look like balls over here, and schematically they're valves as well, and we need to discuss them because they're fairly important. So let's discuss. These are directional valves, and these valves only allow flow to go in one way. So flow is coming from some place. Actually now there's a spring over here, and when the pressure exerted by the flow is high enough, the valve cap will open, and flow can go through the opening and can leave the cylinder. On the other hand, when I have a flow coming from the other direction, well, it can't push the spring up, so it's just blocked over here. And if you do a good design over here, like making some flow channel over here, you can even make the flow fix this cap even better. So that's really something. Some clever engineering can help to make this suit even better. So the flow is blocked. And we usually indicate this by this schematic drawing over here. There's a small ball connected to a spring, only allowing flow to go from this direction, pushing the ball up and moving in this direction. And from the other direction, the flow is blocked. So this is a directional valve, and then we've got these are reduction valves. And these are usually have the layout of, well, the most simple examples of these have the layout of a screw. So by adjusting the screw's depth, we can adjust the amount of flow that goes through the through the valve. And then if you can change the flow rate and even the pressure. And this one is an example that you have to operate with the tools, for instance, using some wrench or whatever. But there's some hydraulically, electrically, or whatever operated as well. So you reduce the amount of flow by adjusting the bulb, the depth of the bulb, and that's shown like this. So by adjusting the thickness of the flow channel, the opening of the flow channel, you can adjust the amount of flow that goes through. And here I have one last example of this. Actually, this one is used by SMC in a double-acting cylinder to make it run smooth. It will otherwise, if you have, there's a flow, let me draw this. There's a flow coming from a certain pump over here, and it's going through this valve, through this hose, and then it's going to directly flow through this directional valve into the cylinder rod side. So over here we have a flow, and of course, if all air was able to flow out directly from here, then we have a large pressure difference because we have a high pressure, P high, over here, and we have a really low pressure, P low, over there. But since there's some rubber sealing and gliders and whatever over here, um, uh, there's something called like a stick slip, so it will move not very smooth. So what they have invented to prevent this problem is to increase this pressure. The pre-low isn't low anymore, but just it's a little higher. It's like an air cushion again, and we regulate the flow going out of this um, uh, out of the head side of the cylinder by this adjustable flow control unit. And of course, it can't go out over here, so that airway is blocked. But over here, it can go out, and it can go out very at a limited flow rate. So there will be some air, there will be some pressure, and since the pressure difference isn't really that high, we have a smoother type of movement of this cylinder. Well, of course, we wanted to show you this phenomenon during the practicals, but well, since we are in a crisis, it's of course not possible. So I hope you can see this happening after summer during practicals. I hope that will be possible. Although I can't promise you anything. So, and I think with this example, I've come to an end of this lecture. So let's just do a quick recap. So during this lecture, we discussed the working principle of hydraulic and pneumatic valves. So we discussed different valves, directional valves, flow reduction valves, directional valves. And you're able to describe the layout of a hydraulic and pneumatic cylinder, and I think you're even able to do some minor calculations onto these. You're able to draw a simple hydraulic and pneumatic diagram, and of course calculate the hydraulic or pneumatic process. You can do some small minor calculations to the cylinders now. So I recommend you to start practicing on this. There's some nice examples and exercises on Canvas. There's one exercise about a riveting process, and the students whoever get the best results compared to the answer, of course, deserves a bar of chocolates. So please send me your answers, and if you send the answers, I will be happy to receive your other assignments as well, to see regarding hydraulics and pneumatics, to see how you perform, not to grade you, but to get an indication of the quality of the lecture and the exercises. So there are some things we didn't tell you about. We didn't tell you about hydraulic pneumatic motors. Usually these are just the reverse of pumps, but in some cases there's some specialty engineering involved. We didn't tell you about gearboxes, hydraulic and pneumatic, and there are lots and lots of interesting applications which we would like to discuss, but I think you can better experience them yourself in some of these practicals. Well, there's some people I need to thank. Of course, I have to thank Jos Persoon from SMC Training and Opleidingen, with who I developed these lectures in hydraulics and pneumatics, and for using the slides. Of course, the book my granddad used. I want to thank the author and the association that made possible this book. And there's there's a lot of images I used, and not all of them I made myself. So I want to thank these internet links as well. And there should be many more, but due to a technical problem, they are not all there. So, and of course, I need to thank you. If there are any questions, please let me know. And for the rest, good luck with the assignments. Thank you.